So a lot of you guys have had questions about double slit diffraction, so I won't go into too much detail. Here we'll be just focusing on the model. So I'm sure you're familiar with two slits. Each of them have their own wavefronts, and there's some screen past them. Past the slit itself, some distance, let's say L away. Now for this case, let's assume the central point is a maxima. So I'm not exactly an artist here, but we see here that at m equals 0, we have a central maxima. Therefore, every corresponding integer will correspond to some intensity maxima. Okay, likewise, we see that every half integer corresponds to an intensity minima. Okay, now what's the equation that models the positions of all these maximas and minimas? Well, it is modeled by this equation: d sine theta is equal to m lambda, where m is equal to 0, 1, 2, blah 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 blah, all those integers. Now let's look at each part of this equation. Lambda over here is basically the wavelength from the 2-point sources. D over here is the distance between the 2-point sources, or the separation between the two slits, often called the slit width or slit separation. And then m as an integer corresponds to any bright spots on the screen if we're talking about light, or any parts where we hear a really loud sound if we're talking about sound waves instead. Okay, but the same equation can be adjusted to represent any of those intensity minimas, meaning any of those silent spots or dark spots, by simply adding a half to our integer m. Okay, now I didn't talk about sine theta yet. So what is sine theta? Well, sine theta is basically the angle between our central point on the screen to halfway between the two slits to some arbitrary maxima or minima. So that was a mouthful, but it might be more easier to represent this on a diagram. So here is some length L, the distance between our slits and the screen, and let's say we take m equals 1, our first intensity maximum, as our point of interest. And what we see here, that some distance y along the screen, we have one leg of a triangle, and another leg of a triangle is basically the same variable L, which is the distance between the slits and the screen, and there is our angle theta. And this is what sine theta represents. So if we're not interested in the angle, or this angle from the central maxima to halfway between the slits to some arbitrary maxima or minima, we can always write this in terms of some other geometric quantity, because we all know that sine theta for a right triangle, as we see it here, can be represented as this expression, which we could get from the Pythagorean theorem. and the generic SOHCAHTOA you guys learn about in high school. However, if we decide to put this expression into our equation for sine theta and solve for y, we see that we're going to get multiple solutions. The issue is we have y squared over here. I don't want to have to go through the hassle of verifying all of those solutions. So instead, let's use a different relationship to look at this triangle. We could resort to SOHCAHTOA, or we could resort to the law of sines, but in any case they will all yield the same equation, all the same expression. And that is y is equal to L tangent of theta. Okay, so now this is an interesting result. So y equals L tan theta. This is an interesting result. Okay, so let's work with this expression over here. So before we decide to go into this expression, let's say we're interested in the points along the screen where there exist only maximas. Well, that's not too much of a difficult task. We just have to take our equation that represents all of our maximas over here and rewrite it as so. We write it as theta as a function of m, arcsine of m lambda over d. Now, if we're talking about our minimum points, we can write it in exactly the same manner. Except, bearing in mind, we have a half that shifts our integer value. So, all in all, if we take the two expressions together and write our final equations for these maxima and minima, we see we're going to get this expressions for the maximum and minimum. Okay, so this is fine and dandy, but remember, there's a condition here. This only works if our central point, where m is equal to 0, is a maxima. So how do I adjust this? In the scenario where my central point is instead a minima. Well, that's not too hard. If our central point is a minima, we realize that every intensity minima is now going to be an integer. And likewise, every intensity maxima will correspond to a half integer. So, in other words, all that really means is if our central point, m equals 0, is a minima, then the labels on these two equations over here just switch. And that's all that really happens. So for our case where the central point is a minima, we can rewrite the equations as follows. Now, the great thing about this is an entire function you could put in the computer. And if you're interested in just the positions of the maxima and minimas, the cool part about all of this is that you're only looking at half integers. So you're going to get a discrete function here. More importantly, if you have a very fancy calculator, you could go ahead and get a whole table of information. And the great thing about this is, we know that theta can only go from 0 to 90 degrees. Or if we're talking radians, 0 to pi over 2. Because if otherwise, no light would hit the screen. So we get a relatively small amount of information here. And we can get all the positions of our maxima and minimas. So using this model, it doesn't matter if we're talking about light or sound. We can determine the locations of all the maximas and all the minimas in a double slit diffraction phenomena. We can even take this the next step and see if we can deal with a triple slit phenomena. That's an exercise that you're welcome to do on your own. But, yeah.